Section 5.2, title is Matrices and Systems of Linear Equations in Three or More Variables. And we already have a little bit of experience in dealing with linear systems of equations, three variables, three equations from a previous section. And this section's probably going to cause a little resentment in the fact that we're doing this one after that section, because with this section what we're basically going to do is learn how to express a system of equations as a matrix, and with that matrix we can enter it into our TI calculators, and it will take care of the row operations for us. It will put it in reduced echelon, or I'm sorry, row echelon form. Okay, so it's going to save us quite a bit of work, but first we have to figure out how do we express the equations in terms of a matrix. Okay, well, we start off with the definition of a system of linear equations, and here we're talking specifically about three equations, three unknowns, three unknown variables, and we have all these different coefficients, A, B, C, and then coefficients for equations 1, 2, and 3. And then we have the constants, the D's. So we've seen this before, and we've used the row operations to solve quite a few of them in the workbook. Okay, well, what we're going to do is for every system of equations, we can extract from it what's called a coefficient matrix, and we can extract an augmented coefficient matrix, which is basically just a coefficient matrix, but it also includes the D's from our system of equations, the constants. Okay, and so this is just in general. The coefficient matrix would be a 3 by 3 matrix, and the first row we would write A1, B1, C1. Simply just the coefficients of the variables. Okay, and then for row 2 of the matrix we would have A2, B2, C2. Okay, the coefficients of the second equation. And then in row 3 the coefficients of the third equation from our system. A3, B3, C3. Okay, all the A's would be arranged in a column, B's would be arranged in the second column, C's in the third, and that would complete the coefficient matrix. The augmented matrix, once you know how to construct the coefficient matrix, the augmented coefficient matrix is the same matrix, except we add a fourth column and we include the constants D1, D2, and D3. Okay, and we can also put these bars here between the coefficients and the constants. And this is sort of a, I guess, a matrix representation of the equal to sign. So in example 1, we'll get a little bit of practice converting our system to a matrix. And for each system, A, B, and C, we want to write both the coefficient and augmented matrix. Okay, with three equations and three unknowns, the coefficient matrix is a 3 by 3. We would list the coefficients of equation 1 in the first row, 1, 3, and 2, and the second equation, 2, negative 1, and positive 1, 3, oh, having a little bit of trouble with my pen, 3, 2, and negative 3. For the augmented matrix, we have a 3 by 4 matrix. we simply just copy the coefficient matrix for the first three columns, and then for the fourth column we insert the constants 8, 1, and 15. And then we can insert these straight brackets in between the coefficients and the constant of each equation. And so there we have the coefficient and augmented matrix. So once again, coefficient matrix 3 by 3, and we're only copying into the matrix the coefficients. We're leaving out the variables. Third equation coefficients go in the third row. Second equation coefficients go in the second row. It's pretty straightforward. Alright, so I was having a little trouble with the other pen program, so I switched. Hopefully my pen will stop acting up on me. But here we are, example 1b, and I've simply written out the coefficient matrix. I copied the coefficients from the first equation to the first row, and so on. And now for the augmented matrix, it will be a 3-row, 4-column matrix. The first 3 columns are just simply the same columns from the coefficient matrix. And for the fourth column, we enter the right hand side of each equation in our system, the constants. Negative 18, negative 12, and negative 4. For our third system, notice in the second and the third equation, we don't have an x or an xy in the third. So those coefficients will simply be 0. So for the second equation, there is no x variable. We enter 0 in the x column, in the first column, for the second row. And the third row, there is no x or y. So zeros for both of those columns, the first two, and then we have a 5 for the z column. And now the augmented matrix. 2, 0, 0 for the first column, negative 1, 3, 0 for the second column, 1, 4, 5, and then a 4, 6, negative 4 for the last column. And we can insert the straight brackets to represent the equal sign in our matrix form. So now that we know how to go from a system of equations to the augmented matrix, what we'll do is we'll do the reverse. We'll go from augmented matrix back to a system of equations. So the first column are the x coefficients, the second column are the y coefficients, third column are the z coefficients, or we can call the first column A's, B's, and C's, and then the last column we have the constants, or the D's. And so this first row would be translated to the equation 2x minus y plus 5z equals 3. The second row would be negative 2x plus 3y plus 4z equals 0. And the third row, simply an x minus 7y plus 8z equal 2. And that would complete part A. Part B, notice we have the straight bars. Those are the equal signs for our equations. Here we just have a system of two equations and two variables. So these are our x coefficients in the first column, y coefficients in the second column, and there is no z column. Okay, and what indicates that are these straight bars, the straight brackets in between the last column and the second column. Okay, so when you see these, you should know that these numbers to the right represent constants, and we can call these C's. So this first row would translate to a 2x minus a y equal to 5, and the second row would translate to a negative 2x plus 3y equal to 0. And as we usually do with systems of equations, we put the curly bracket on the end, and we could insert that at any time. Okay, moving along. Row echelon form is what we strived for when we were working with the systems of linear equations. Okay, and row echelon form, when you're dealing with matrices, is easily recognizable in that all of the entries below the principal diagonal of the matrix are zeros. Okay, so below in example 3 we have 6 matrices, and we want to recognize the ones that are in row echelon form. So if we look at the first one, first thing you want to do is pick out the principal diagonal, and to do that for a matrix you simply start with the first element in the first row in the first column. In this case it's this 1 here, the top left corner, and then you simply go down 1 over 1. You circle the diagonal, okay, and it ends here with the 2. So 1, 3, and 2 make up our principal diagonal. If you look below the principal diagonal, we have 0, 0, and 0. All of the entries are 0 below this diagonal, and so this matrix is in row echelon form. Okie dokie. B, our principal diagonal is 2, 3, 2, 1. And this particular matrix would actually represent a system of equations that had 4 equations because we have 4 rows, and then we would have 1, 2, 3, 4 variables. Okay, we haven't actually seen or dealt with a system like that before, but that's what this matrix represents. And if we look below the principal diagonal, all of our entries are 0. So this likewise is in row echelon form. For C matrix, our principal diagonal is 2, 0, 8. However, the entry -2 below that causes it to not be in row echelon form. Not row echelon form. Alright. D is a small one. It's a 2 equation, 2 unknown matrix. And our principal diagonal is 2, 3. And we only have 1 entry below the principal diagonal, and it is 0. So this matrix is in row echelon form. C, we have 2, -3, 0 for our principal diagonal, and then if we look below that, we have all entries are zeros. So again, this is reduced, or I'm sorry, row echelon form. And finally, for F, we have principal diagonal of 2, -2, 0, and again, all of the entries below that are zeros, and so this is in row echelon form as well. And if you glance at the bottom row of each of these 2 matrices on the bottom, you should recognize that this matrix represents a system of equations with no solution. Very easy to pick out. Okay. On the left side, we simply have 0. The bar indicates an equal sign, and then on the right side we have 2, but 0 does not equal 2. Okay, so this matrix has no solution. And then for the last one, our third row is simply 0 equal 0. And so this matrix represents a system of linear equations with infinitely many solutions. Doesn't mean that we can use any x, y, and z combination. It just means that there are infinite number of combinations that will satisfy this particular system of equations. Okay. So in example 4, we are given A, B, and C. We're given matrices that are already in row echelon form. And so to solve these systems that these matrices represent, when it's in row echelon form, we can simply just apply back substitution. And so we start with the last row. The last row of this matrix represents 3y equal -4. And to get the y by itself, we would simply divide by 3. Okay. Now that we know the y variable, we can take it back to the next row above it, and that would give us 2x minus a -4/3. Okay, this is a -1 times y here, so I would have a minus y, but y would be replaced with the y that we found from the last row. So I'd insert a negative 4 over 3. Then I arrive at this vertical bar here, and that represents the equal sign, and then I simply have the constant 5. Okay, so now we solve this equation for x, and we get 2x plus 4/3 equals 5. If we subtract 4/3 from both sides, we would have 3 or 15 over 3 minus 4 over 3. That would give us 11 over 3. So not very nice numbers to play with. But now all we have to do is divide by 2. Or multiply by half, same thing. And we get x is equal to 11 over 6. For matrix B, the last row would give us 2z, because the 2 is in the third column over, but we haven't passed the equal to bar. And so being in the third row on the left side of the bar means that this is a coefficient, and being in the third column means that we are dealing with the variable z. And the entries in the matrix to the right of the vertical bars are the d's. So the third row translates to the equation 2z equals 4. We divide by 2, and we get z is equal to 2. We take this and we put it in the second equation. The second equation comes from the second row. Translating from the matrix, we would have 3y plus 4z equals negative 1. We substitute z equals 2 into this equation, and we have 4 times 2. Subtract 4 times 2 is 8. If we subtract 8 from both sides, we get 3y by itself and a negative 9 on the right. And now if we just simply divide by 3 on both sides, we find that y is equal to a negative 3. And so we have part of our solution now. We have the z and we have the y. And at this point, we would substitute our z and our y into equation 1. The first equation, first row. So, what would that look like? Well, we have a 1, the coefficient of our x, so we could just simply write x, positive 2, or the second column in the first row, so that would translate to a plus 2y, and then a plus z equals 3. Substituting our values of y and z into the equation would give us 2 times 2, and oh, hold on, my y is actually a negative 3, and then my z is the 2, and so here we have an equation with x being the only variable. We isolate the x on one side. 2 times negative 3 is a negative 6, plus 2 is a negative 4, so we would have to add 4 to both sides, and we would end up with a plus 7. and that would complete our solution. Our solution to this matrix in B part would be a triplet 7, -3, 2. Okay, and here we have a system of equations with 4 unknowns and 4 equations. I know that because we have 1, 2, 3, 4 rows for 4 equations. And here is the bar indicating where the coefficients stop and the constants begin. And we have 4 columns in front of the vertical bar here. And so that means we have 4 variable columns. This being the X, Y, Z, and I'll call this 4th one W. Alright, we haven't dealt with a system like this, but with the matrix being in row echelon form, the last equation, we start with that, and that'll give us 1 variable, and then we just simply back substitute that variable and all of the other ones that we find until we get to the first one. With the coefficient of the W being 1, there's not really any work to do on the equation from the 4th row. We simply find that W equals a -2, and we back substitute that into the 3rd equation from the 3rd row. The 3rd row translates to a 2Z plus a 3W equals 4. Plugging in our value of W -2 and isolating the Z will give us a Z equals 5. So I guess we could call our solution a quadruplet, since we're going to have 4 variables, X, Y, Z, and W, and we've got 2 of them already, so we're halfway done. Now we take our Z and W and we go to the 2nd row. Our 2nd equation translates from the matrix as 3x plus 4y minus 2z equals -3. So it's a big matrix, and it's 4 equations, but not really that much work. Okay, as long as you take your time and you start from the bottom, and if you start with a matrix that is already in row echelon form. From here you just use back substitution. So we plug in our values for y. Oh, I used the wrong variables. Okay, this first one is supposed to be a y. I'm used to doing the 3 equations and the 3 unknowns, and I'm sure you are too. But this 3 should have went in front of a y, and the 4 a z, and then the 2 a w. So I need to put in my w and my z. So hopefully you pick up on that like I did. Correct it before you get too far into the problem. We solve for our y, and we have on the left side 4 times 5 is 20, plus a 4 is 24, and that's a positive 24 that we would have, and so we would have to subtract a 24 from each side to get the 3y by itself. 3 minus 24 would be a -21. Divided by 3, we'll get a -7. And now we're ready for our first equation and to solve for our x variable. For our first equation, the x has a coefficient of 2, Y has a coefficient of -1, Z a 3, and W a -1. So I can just simply write negative W. And then my constant is a 4. So I would have minus a -7 plus 3 times Z, which is a 5, and minus a -2 for a minus W. We get the 2x by itself. We have a +7 and a 15, which gives us a 22, and then +2 would give us a 24. And so we would subtract 24 from both sides, giving us the equation 2x equals -20. And then we divide both sides by 2, and we find our x value, which is -10. So to put it all together, we would have the solution -10, -7, 5, and -2. Alright, but as you already know, the real work comes into play whenever you start out with a matrix that is not in row echelon form. So, like I said earlier, what we're going to do in this chapter is we're simply going to use these $180 calculators that we have, the TI calculator. And first, we will do a little bit of work in that we're going to translate this system of equations into a matrix. And the matrix is actually what we're going to put into our calculator. And then from our calculator, we will have row echelon form. Alright, so it's going to do the grunt work for us. The first row would be 1, 3, -2, 8, 2, -1, 1, 1, and 3, 2, -3, 15. Alright, and we learned about our calculators and entering matrices into it in the previous section. So simply turn my calculator on and hit second matrix. You can glance down through the column of matrices that we have here, and you see that they're all empty because we don't have any dimensions listed out to the side. So we can put this in any spot that we want to. But to enter a matrix, we have to go over, arrow over to the edit screen, and I'll just put it into the A spot. And so I hit enter for A. The calculator prompts us to enter the dimensions of the matrix, which is 3 by 4, 3 rows, 4 columns. And then we just proceed in entering the elements of our matrix. A little time consuming. It can't read our workbook and enter the matrix for us. But it's definitely saving us a lot of frustration because, you know, me myself, I make mistakes when trying to get the equations in row echelon form. It can be pretty tough sometimes, especially if you start getting variables that work out to be fractions and not whole numbers or integers. Alright, so we can trust our calculator to give us row echelon form. So first step, enter the matrix into the calculator. We're finished. And so we go, we hit second quit, get back to our home screen. And now what we want to do is call to our home screen a matrix operation and it is listed under the math screen of the matrix menu as ref, reduced echelon form. And so we scroll down to A, we hit enter, and it takes it back to the home screen. And now we go back to our matrix menu, and under the name screen we select the matrix that we want to perform the ref operation on, which is A. You can see that you have the dimensions listed out to the side of A. That's the one that we used, and so we hit enter and enter, and here we are. Okay, and you may also notice that we're given decimals, and we don't want to work with decimals because we want an exact solution. We don't want to approximate it. And so if you look at your matrix after you use the row echelon form function or operation, whatever you want to call it, if you have decimals, then you can take your calculator and use the fraction operation under the math menu, hit enter, and it will change all of those decimals into fractions, exact numbers. And we want exact numbers, not rounded numbers, because we want an exact solution. We don't want to estimate our answer. Okay, and you might also notice that the calculator gave us a specific type of row echelon form, and that all of our principal diagonal elements of our matrix are 1. And this this could make this a little easier, or it could make it difficult in that we have these fractions. But sometimes there's just no avoiding dealing with the fractions. So calculator just did a whole lot of work for us in a short period of time, but we're going to take it from here now that we have our row echelon form, and we are going to back substitute. The third, we could enter our bars, and notice that the calculator didn't put bars separating the third and the fourth column. You just simply have to know that they're there. And so we have X column, Y column, Z column, and then our constants. So our third row translates to Z equals -3. So it was nice to have that 1 there in the principal diagonal. But now we take this Z and we put it in our second equation from the second row, and we have a Y minus 3/7 times Z, which is a -3, equal 9. Alright, so it gets a little messy here. We have to deal with fractions, but -3 times a -3 would give us a 9/7. We would subtract 9/7 from both sides, and we would have a Y equals, let's see, we want to write 9 as a fraction with a 7 on the top, so we multiply a 7 on the bottom. We multiply 9 by 7 and get 63, and then we subtract 9/7 from it. This 9/7 came from the left side, so we get, let's see, 6 from 60 is a 54/7. And I think we're just stuck with that fraction, huh? So, bring up my calculator real quick. I don't think that will reduce. Nope. So Y is 54/7, and so now we take that back to the first equation. We won't have to deal with the fractions too long because this is our last step. But we do have a 2/3 Y. We have a minus Z, and all of that equals 5. We plug in our numbers 54 over 7 minus a minus 3. Alright, let's see. 2 times 504 would be 108. 3 times 7 is 21. Plus 3 equals 5. So I don't want to get bogged down with the fractions. We've already used our calculator to do the matrix stuff, so what I'll do is I'll just skip over here, and what I want to do is solve this equation for x. And so what I'm going to end up doing is subtracting 108 over 21 and 3 from 5. Okay, so let's see, 5 minus 108, let's see, 108 over 21, I can't get to my calculator because there's writing over the top of it. Let's see if I can erase some of this stuff. So hopefully you have this copied down in your workbook. Okay, 108 over 21, and then we have minus 3. Enter. And gives us a decimal, so let's see if we can switch this over to a fraction. Negative 22 over 7. That completes our solution. We've got some nasty fractions in there, but our end solution is negative 22 over 7. Let's see, y is 54 over 7, and then z is a negative 3. Okay. I had a plus 6 there. Wait, no I didn't. No I didn't. I had a minus, yeah, I had a plus 3. Okay. Yeah, this is right. I was looking at the equation instead of the first row. This should be right. Of course, you can always go back and double check it with your equations. And so that completes part A. We will scroll down the page and work another one. This one should be a little more manageable. The matrix that we need to translate this to is going to be a 2 by 3. Our coefficients are 3, negative 1, 2, 3, and then we have constants of 7 and 1. This is what we're going to put into the calculator. Okay, and instead of going back and erasing A, we'll just put this one in the B spot. It is a 2 by 3. Elements are 3, negative 1, and 7, and 2, and 3, and 1. Enter. And now we go back to the home screen. We call out our, I went to the wrong screen. I need to go to the matrix one. Call out the math operation ref for reduced echelon form. And now I go back to my matrix screen and I select B matrix. and I simply hit enter. And I notice that I have some crazy decimal numbers that I don't want to approximate. I don't want to round those, so I go to math. I select the first operation, fraction, hit enter, and it changes all of those decimal numbers to exact fractions. So exact numbers, no approximating. Here is our row echelon form. Row echelon form, and from here we do the work. We back substitute, and so this second row represents our second equation. The last column are constants, and so we have a x and a y for the variables. 1y, vertical bracket, vertical bar here represents our equal sign, so y equals -1. We take that and substitute it into the first row, which represents our first equation. Our coefficients are 1 for x, -3rd for the y, but the y is a -1. So instead of writing y, just put in a -1. And here's the equation I need to solve to get the last part of my solution, the x. So I get x plus 1/3 equals 7/3, and if I subtract 1/3 from both sides, I will get x equals 6/3, which is a 2. And so my solution is an ordered pair, 2, -1. And so here we are. Last 3 examples of this section. All of them are, none of them are in row echelon form. We just glance down through here. Every variable in each equation has a coefficient. So our matrix, augmented matrix, will be 2, -5, 3, bar, -18, 3, 2, -1, -12, 1, -3, -4, and -4. And now we go to the calculator. Alright, I'll go back and edit A. Okay, it's still a 3 by 4, but the elements have changed, so I have to go through each one. First one's a 2 on the first row. Then I have a -5 for the second column, a 3, enter, -18, enter, 3, enter, 2, enter, -1, enter, a -12, and that completes the second row. 1 for the third row, -3, second column, -4, and -4. So the only thing that can go wrong here is if you just hit a key, type in the wrong number. So be careful. Know that from experience. We want row echelon form, so we go back to the matrix screen. I would always suggest once you get through entering the matrix to go back to the home screen and then back to the matrix screen. So we pick the ref operation. Which matrix do we want to perform that on? A. You can close your parentheses, enter. We have decimal numbers. Go to math to fix it and select fraction, enter, and there we are. Row echelon form. We have 1, 2/3, -1/3, and a -4. 0, 1, -11 over 19. Very ugly numbers here. 30 over 19. And then our last row, 1 and -1. So that one's going to be nice. All the other ones, not so much. Alright, and so you got a matrix. First 3 columns of this one, a 3x4, will be our coefficients, and then the last column, our constants of the equation. We start from the bottom and work our way to the top. We only have a 3rd column, and in this case that's a coefficient column, so we have a 1z here, and that equals -1. We back substitute that into the second equation, which is a y minus 11 over 19 equals 30 over 19. Alright. I didn't put my z in there. This is 11 over 19 times z. Alright, what was our z? Well, it was a -1. So maybe this isn't going to be too bad, because we end up with the same denominator. But this is a plus 11 over 19, and so we have to subtract that from both sides to get our y by itself, which is going to give us a y, 30 minus 11, 19 over 19. So y is 1. A lot better than what I thought it was going to be. Okay. Now we take our y equals 1 and our z equals -1, and we put it in the first equation. So we have x plus 2/3 times the 1 minus 1/3 times the -1 for z. The -1/3 was in the 3rd column, and that's the z. So I multiply that number by z, and I get a -4. Okay, so I have x plus a 2/3 plus a 1/3 equals a -4. Well, a 1/3 and a 2/3 just 3 over 3, which is a 1. And to solve this for x, I just subtract 1 from both sides, and that will give me an x of -5. So the solution here is -5, 1, and a -1. Alright, so same drill. D, take the system of equations, translate it into an augmented matrix. Let's go ahead and write all this out. Here's our matrix. We could put in our vertical bars to represent our equation or equal signs. But now we go to calculator. We're on the home screen, so I want to go to the matrix, and I'll write over A again. Still a 3x4, but our elements of the matrix are different. So first one's 1, 2, -2, 3, 5, 8, negative 2, 14, 3, 4, negative 2, 8, and we're done. So once we hit enter on that 8, the calculator has accepted these entries for this matrix. So I would suggest you hit second and quit, go back to the home screen. And now we want to put this matrix in row echelon form. So we call this matrix operation from the matrix menu, second matrix, over to math, down to A for ref, enter, and back to the matrix screen and select our A matrix, enter. And we have decimals. We can work with that. Okay. Let's see here. We have 1, 1.6, negative 0.4, and 2.8. The second row is 0, 1, 1.5, and the last row is 1 and 0. We're finished with the calculator. The calculator has done its part. Now what we have to do is bag substitute, starting with the last row. Last row translates to a z equals 0, a 1z. This isn't 1 equals 0, this is 1 times the z because we're in the third column. And so only the last column is a constant, and we happen to have 0 for the constant. So 0 on the right hand side, but we have a 1z on the left. So z equals 0. We back substitute that into the second equation, which results in a 1y plus a 1z equals 0.5. So y plus 0 equals 0.5. That was definitely not bad at all. You could say y equals a half. But now we take the y and the z that we found and we go to the third, not the third, but the first row, first equation. Alright, and that is, this was a 1.6. I don't know why my decimal wouldn't go in there. 1x, 1.6 times the y, and we found our y to be a 0.5, minus a 0.4, but z is 0, so that doesn't make a difference. And I didn't give myself enough space to work with, so I gotta erase that. And all of that has to add up to 2.8. So x, half of 1.6 is 0.8. And the 0.4 drops out because I multiply it by a 0. And now if I subtract 0.8 from both sides, I get x equals 2. And that completes my solution. It's a triplet. X is 2, y is a half, 0.5, and z is a 0. Alright. And this last one. I'm going to show you something with the calculator that is going to make you very happy. But first, we can't get around sort of doing this step. You could go straight from the linear equations to the matrix in the calculator, but I always like to write it out first. 3 and negative 4, negative 1 and 1, 2, negative 3, 1 and 1. These aren't bars, these are ones, so maybe I should make it a little bit more fancy one. here's my bars for my equal signs: 1, -2, 3, and 2. Alright, so got a little sloppy there, but we go to the calculator and go to the matrix screen. I go to edit. You always go to edit to put the matrix into the calculator. I'm going to write A with the new elements: 3, -4, -1, 1, 2, 3, 1, 1, 1, -2, 3, and 2. Enter. Alright, so I've hit enter on this 2, it accepted it, and hit second quit and go back to my home screen. And now I'm going to show you the magical double REF. Okay, don't tell anybody I told you about this. It's got to be a secret between us. Alright. It is another matrix operation. So we go to math and we go down, and it is right below the REF that we've been using, reduced echelon or row echelon form. And the reason why this whole time I've been saying reduced is because double REF stands for reduced row echelon form. This is the nice one. So we hit enter, and we go back to the matrix screen, and we hit enter to insert A into our double REF operation. Enter, and we basically have the answers given to us. And we can turn them into fractions the same way we have been. But what do we have here? We have a matrix with only ones in the principal diagonal and zeros everywhere else. So each row only has one variable. We have our X, Y, and Z variable, and then we have what they equal in the fourth column. Now, with this being said, you may be required on the test to show your work, and if that's the case, then what you have to do is take it to row echelon form, and then do back substitution. I don't want you to simply use double REF for show your work problems on the test. But at least I showed it to you, and once you get done back substituting, you can check your answers. Okay, but if you haven't realized by now, from what I told you, we do already have the answers. This matrix translates to 23 over 60 for X. Y is -1 over 12. And Z equals 29 over 60. And so that completes section 2, chapter 5. Thanks for watching.